Good afternoon. Today we will be reviewing the aerobic and anaerobic biodegradation of 1,1-dichloroethylene, more simply referred to as 1,1-DCE. 1,1-DCE does not naturally occur in the environment, it is a manufactured compound. It's a liquid with a mild, sweet odor. 1,1-DCE is a volatile organic compound that is toxic to humans. Most common routes of potential exposure are through inhalation or consumption of contaminated drinking water. At least 610 of the more than 1,850 past and present EPA National Priority List sites contained 1,1-DCE as a contaminant. 1,1-DCE is primarily used in the manufacture of adhesives, refrigerants, food packaging, and coating resins. Spills at facilities that use 1,1-DCE can introduce it into the environment. 1,1-DCE can also become present as a daughter product of tetrachloroethylene, trichloroethylene, or 1,1,1-trichloroethane. There are several different degradation pathways which involve 1,1-DCE. Here, we will be focusing on the two depicted. As mentioned, 1,1-DCE is a daughter product of PCE, TCE, and 1,1,1-TCA. 1,1-DCE can then be further reductively dechlorinated, becoming vinyl chloride, then ultimately ethene. Or, 1,1-DCE can be oxidized and then further metabolized, ultimately producing carbon dioxide, water, and chloride ions. So, one of the mechanisms for biodegradation of 1,1-DCE is aerobic biodegradation. This process includes aerobic metabolism and aerobic cometabolism. In the presence of oxygen, microorganisms initiate degradation by attacking 1,1-DCE molecules, often through oxidative dechlorination. The next steps are dehydrohalogenation, oxidation reactions, and metabolic transformations leading to the breakdown of compounds into simpler forms like carbon dioxide, water, and chloride ions. In aerobic metabolism, microorganisms directly consume 1,1-DCE as a source of carbon and energy, and usually leads to more complete degradation of the 1,1-DCE compared to cometabolism and produces non-toxic end products. But in aerobic cometabolism, microorganisms use a primary substrate for growth while accidentally breaking down a pollutant like 1,1-DCE. Enzymes possessed by microorganisms act on both the primary substrate and the 1,1-DCE with different affinities. For each mechanism, specific microorganisms are involved. For instance, Pseudocardia sp-D17 for aerobic metabolism and Azoarchus sp-DD4 for cometabolism. D17 breaks down 1,1-DCE in the aerobic metabolism process. Because this bacteria doesn't need primary substrates for growth, this indicates that the bacterium directly consumes 1,1-DCE as a source of carbon and energy for growth. In this metabolism by D17, specific enzymes are involved in the degradation of various chlorinated ethenes, including 1,1-DCE. These enzymes, such as propane monooxygenase, toluene monooxygenase, and catechol 2,3-dioxygenase, are typically associated with metabolic pathways rather than cometabolic processes. The aerobic biodegradation of 1,1-DCE by DD4 happens in a cometabolism process. The bacterium utilizes propane as the primary substrate for growth and the degradation of 1,1-DCE co-oxidized as a secondary process. I should mention that Azoarchus sp-DD4 is isolated from activated sludge, which is rich in diverse microbial communities capable of cometabolic transformations. Reductive dechlorination is an anaerobic process carried out by bacteria containing reductive dehalogenase enzymes. The enzymes allow the bacteria to cleave the carbon-chlorine bond. The chlorine is then replaced with a hydrogen. 1,1-DCE is utilized as an electron acceptor, thereby being reduced during the process. This is a main mechanism responsible for the success of monitored natural attenuation of chlorinated ethenes in groundwater. Several bacterial groups have shown the capability of carrying out reductive dechlorination. However, Dihalococoides is the only genus which contains strains that can fully dechlorinate PCE to the non-toxic ethene, which includes the dechlorination of 1,1-DCE. Listed as examples here are strains 195 and 11G. Although not all strains are capable of full dechlorination, a mixed microbial community can, in conjunction, complete full dechlorination. And many of the strains capable of reductively dechlorinating 1,1-DCE have ethene as an end product. Dechlorination can occur very quickly, within days in ideal conditions. However, high concentrations of PCE have shown to inhibit the formation of ethene, causing vinyl chloride to accumulate until the PCE has been consumed. With aerobic metabolism, certain microorganisms exhibit the capability to degrade 1,1-DCE. However, efficiency can vary based on initial concentration, presence of co-contaminants, or the suitability of the microbial community. Vinyl chloride or 1,1-DCE epoxide are intermediate byproducts, which can accumulate or be further metabolized and completely mineralized. With reductive dechlorination, several bacterial strains show the ability to fully degrade chlorinated ethenes to the non-toxic ethene. Full dechlorination can occur very quickly, within days in ideal environments. However, elevated PCE concentrations have shown to inhibit the formation of ethene until the PCE has been consumed. Vinyl chloride is an intermediate byproduct, which can accumulate or be further dechlorinated, becoming the ideal end product ethene. Thank you. We hope you learned something new about aerobic and anaerobic biodegradation of 1,1-DCE.